Okay, hi everyone, and welcome back from the break. Next up, we have Mario Cao from SEDA, who will be speaking about designing a multi chain native decentralized Oracle. Welcome, Mario, everybody.
Okay, hi everyone. I'm Mario. I work at SEDA Protocol. And first of all, I want to thank you for coming to this presentation and also to the organizers to making this conference happen. During today's talk, I'm going to talk about what we have been working during the last year, which is a cross-chain decentralized Oracle. And I hope after this talk, you can have like a better understanding of it. So the outline for today, we are going to start. I'm going to start talking about where we come from. Then I'm going to jump in directly to what we have been building and how we are achieving the goals we set for it. And then I'm going to focus more on one of the building blocks, which is the bridges. So and then at the end, if there is enough time, I'm going to do a quick progress check where we are in the project and also the next steps regarding protocol improvements that we can build on top of the SEDA protocol. So our origin story started with Flags protocol. Before SEDA, we work at Flags. Maybe rings a bell to any of you. So and basically at Flags, what we built was two products. One was the third-party Oracle first, and then a first-party Oracle. I like to think that those two products are pretty orthogonal in their design considerations. The first one was we went down the road of decentralization, and we managed to have like a generic Oracle with a hybrid also with some prediction market, because you could also query any generic data, but also make like questions and answers. But we have a big problem was like latency. So because we had like a dispute mechanism on top, it was pretty slow, and we were not really fulfilling the needs from some potential contracts protocols using it. So that's the reason why we thought we have to do another product, and we built a first-party Oracle, which was like the opposite, assumptions. Like we tried to build something that was pretty fast, but on the other side, it was pretty centralized. And as you all know, centralization normally means that some components are single point of failures, and it's something that me as a protocol builder, I don't like, I don't feel comfortable with. So, and also I just wanted to highlight that we managed to make quite the success with this FPO. In reality, last year, for a period of time, we managed to secure like over $3 billion, which was like insane for us. But it made us think like maybe it was not the right approach, because this cannot scale, horizontally. And that's one of the main reasons why we decided to build SEDA protocol. So what do we want to achieve with SEDA? In reality, I like to think like it's something beyond an Oracle. It's something more like a data transport layer. In my past, I was also like a networking engineer, so I like to feel like to think like about SEDA protocol as a HTTP for Web3. I would say even HTTP on steroids, because it's not only fetching data, but also having computation on top after fetching the data. So on the right side, we have some of the goals, design goals that we wanted for SEDA. And first of all is any data. So we want to query not only price feeds, as we focus with our FPO, but anything. We want also to be able to integrate with any chain, so any rollup, any layer 2, anything. That is, here the small letter is like a smart contract capable chains, okay? And then something that is right now paramount for us is like it should be usable by anyone. Not only querying data, but also anyone should be able to participate and join the network. It doesn't matter if it's like a node operator, a data request executor, anything. So the idea here is to have like to build a system, a protocol that is decentralized and permissionless. And the last 2 points are more non-functional requirements, in the sense like because of our previous experience with the third-party Oracle, we want to build something that is really fast. We are building this protocol in a way like it's going to be executing data requests in a matter of minutes. So we need also to be able to go to any chain also with that kind of finality. And the last point, I think it sometimes is disregarded by many protocols, not only oracles, but many protocols, is like it has to be economically sustainable. It means not only being cheap to query data, but also all the parties within the protocol, they should have an alignment of interests. So how we are going to achieve this? This is an oversimplification, okay, of the protocol, but I only had 15 minutes. So the first building block is the settlement layer. In our case, we're going to build our own chain. It's a deflationary proof-of-stake network. And sitting on top of it is going to be an overlay network. It means a network that is going to be much higher in the number of participants, which main responsibility is to fetch the data and report the data back. Okay? The way it's going to work is with a crowd attestation mechanism. So it's going to be thousands of participants. And for each data request, a secret and random committee is going to be selected. So there we have these secret random committees. And on top of that, how they fetch the data, where the WASM execution environment comes in. So here's the idea that all data request executors, they will have the capability of launching a virtual machine and executing some binary, WASM binary, that will fetch the data. And then it's going to be also another WASM binary that will aggregate the data from different reporters. And the last building block of the stack is the fast finality bridging. So we built this amazing stack, but if this is really performant, we also need the last of the building blocks also to be really fast for that. And because I'm a researcher and I'm an engineer, it was really mandatory for me to include also this other building block, which is shared by all the components, that are economic incentives and cryptographic mechanisms. For example, for these secret random committees of the execution overlay network, what we need is a cryptographic sortition, which is being done, for example, through a verifiable random function. So if we take a look to architecture, it's also a little bit simplified. We want SEDA to be a protocol sitting on the bottom, and that can be used and giving service and operation to many other protocols. It doesn't matter if it's like a layer 1, a subnet, or a rollup. The important things like these protocols will interact with the SEDA chain with the use of some relay contracts. And the way these relay contracts are going to be connected to the SEDA chain is through some entities that we call relayers, but many other protocols call them bridge nodes. And they will be forwarding messages from these relay contracts to the SEDA chain back and forward. And then, as I tried to mention before, it's really important to highlight that this data is going to be fetched and executed in an overlay network that is sitting on top, in this case, on the side, to the SEDA chain. Okay? And then the other thing that I mentioned, like these data request executors will be fetching the data and reporting back the results to the SEDA chain as transactions. And then these transactions are going to be aggregated into one single data point by some WASM execution that is performed by the main chain validators. OK, focusing more in the last building block, which is the bridging. Obviously, we want a simple design, but we also want a cost-effective design, to be able to integrate with any chain in a matter of days. And here, the trick is we need to comply and to satisfy also the same goals we wanted to do to have in the SEDA protocol. It means these bridges should be supporting any data. This thanks to the WASM binaries, should be flexible and generic. They should be able to be on any chain, in reality, that is smart contract capable, thanks to the relay contracts. And in the same way, we need some bridging mechanisms that allows us to have a really fast finality. And in the next slides, I'm going to show a diagram that I hope is going to help to understand this better. And the last part, which is also really important, is these bridges should be runnable by anyone. Again, we want to build a permissionless protocol that if a relayer shuts down, any other relayer can hop in and take the job of relaying messages. The idea here is like no relayer, no single entity should have the power of censoring any message passing. And obviously, all of this works thanks for having cryptographic verifiable mechanisms in order to achieve this trustlessness of the protocol. So, bridging, I have two diagrams. One is from any chain to SEDA, and then I'm going to have another one SEDA to any chain. So starting off on the left side, we see some protocol contract, and this direction consists of 3 steps. Okay, the first step is the protocol contract submits a data request to a relay contract, indicating which wasm binary should be executed, and also adding some parameters and arguments. Also, they will append some rewards for the forwarding service. Then the second step is the relayer, monitoring this contract, and if the rewards are enough, it will pick that data request and forward it to the SEDA chain. In the third step is this forwarding happening. It's just wasm binary and parameters. But here the main trick, in order to achieve finality, is that they are covering the execution cost. Okay, under the promise, like later when the result comes back, the relayer will be paid. I didn't mention it, but obviously data requests, wasm binaries and parameters are protected by some unique identifier that is computed with a hash function. So if the relayer tampers with the data request, most probably he will end up, no, for sure, he will end up paying for a data request that nobody's going to use, and it will never get a reward. On the opposite direction, so here we have to imagine like the data request has been resolved, magic happened, SEDA protocol. And then the monitor will be doing something similar. It will monitor in the SEDA chain for this result to be there. And once it's there, it will forwarding the data result to the relay contract. Here, the small letter is not only forwarding the data result, but also some cryptographic proof that ensures like the data request has not been tampered with, and also that it comes from the SEDA chain. I don't want to go too deep into that, but using some aggregate signature scheme that ensures like it comes from the SEDA chain. And the last step, it's just the protocol contract reading the data, or maybe we can, as many other Oracle protocols, we can have like the relay contract calling to some callback function on the protocol contract. So progress check. Right now we are focusing on the core protocol. So we are, as I mentioned, we are building our own chain. So right now we started working a few months ago. So the things like we are working on this settlement layer. We are working on this overlay network. So building all this cryptographic sortation mechanism, implementing these different transactions for having, for example, like a commit and reveal scheme. So data request executors cannot free write and copy from each other to mitigate some attack vectors. But also, it's interesting that we are also working on SDK libraries and tooling. The idea here is like in the next month, we aim to launch some testnet. And the idea is like to onboard as soon as possible all developers and try to gather feedback, what's missing, what are the pain points, and so forth. And the next phase is, this is oversimplified decentralization and tokenomics. That's why this owl is there. So the idea is like, first we focus on the core protocol, then we, check like everything. We don't have single point of failures, that the security assumptions hold, that everything is working as it should, and then we have to find, the proper configuration so that the tokenomics hold and all the parties in the protocol have the incentives aligned. And that's my last slide, and I think it's my favorite one. Okay, we are building SEDA in a way that it will be a piece of infrastructure, to connect external data to any other chain. And the idea is like we want to build it in a way that is super easy to create more advanced features and services on top of it. And we saw it today, during the panel, like Oracle's structural value is one of them. Our thesis is like if one of the first things we want to build is OEV. So the idea is if we could attract part of the revenue that is created from Oracle data and the opportunities created from Oracle data, it will revert really into the protocol by, for example, partially subsidizing data requests and also, helping the protocol itself. So this is something really, really positive that we want to do as soon as possible. And the two other points, anchor nodes is an optional feature. The idea here is like to have like an optional mechanism for protocols that are using SEDA, to have like a circuit breaker and a fail-safe mechanism. I don't want to go too much into detail to that. If you have questions, we can talk later. And the last one is authenticated data sources. So all what I explain is generic, any data, everything. But we know, for a matter of fact, that there are many data providers. They make some business from their endpoints. So the idea here is like how we can onboard them into our ecosystem and making some incentives for them, to have some revenue from the data. That's everything from my side. I hope you enjoy it, and thank you very much.